everyone. So we completed the design part of FIR filter. So today we will start with the structures of FIR filter. So in order to realize FIR filter, we have 4 different structures. So the first structure is direct form realization. The first one is direct form realization. The second one is cascade realization. Third one is lattice realization. And the last one is parallel realization. So in our syllabus we have only direct form realization, cascade and lattice. So today we will start with direct form realization, then we will see cascade realization, and then we will move on to lattice realization. Okay. So these are nothing but the different types of structures with the help of which we can realize an FIR filter. So we will start with direct form realization. Starting with direct form realization. So if I write the equation for y of n for an FIR filter, we know it is given by summation k ranges from 0 to m minus 1 bk into x of n minus k. So let us term this as equation 1. And we all know the value of h of k, we know that the value of h of k is same as bk, that is the filter coefficient, when the range of k is from 0 to m minus 1. So in the equation 1, instead of bk, I can replace it with h of k. Therefore, y of n will be equal to summation k ranges from 0 to m minus 1 h of k into x of n minus k. Okay. Now what let us do? Let us expand the summation and let us see what is the equation for y of n. So if I expand, y of n will be equal to h of 0 into x of n minus 0 will be x of n only, plus h of 1 into x of n minus 1 plus h of 2 into x of n minus 2. Similarly, up to x of, what is the last value? It should be m minus 1. So it is h of m minus 1 into x of n minus m minus 1. So this is nothing but the equation which we obtain by simplifying the equation of y of n by substituting bk as h of k. Okay. Now with the help of this difference equation, what I need to do is I need to draw the direct form structure. So looking into this particular equation, we know y of n is nothing but the output, x of n is nothing but the present input, x of n minus 1, x of n minus 2, x of n minus m minus 1 are nothing but the previous input, and h of 0, h of 1, h of 2, h of m minus 1 are nothing but the filter coefficient. So keeping these things in mind, let us start drawing the structure, that is direct form realization. So the input is x of n, I am taking the input as x of n. Okay. So x of n should be multiplied with h of 0, correct? So I will branch this, x of n should be multiplied with h of 0, then it has to be given to an adder, yes. So let me connect this to an adder. Okay. So what is the input here? Here it will be h of 0 into x of n. The first term is done. Moving on to the second term, here x of n is delayed once. So let us use a delay unit. So if I use the delay unit z inverse, so what is the output of this? So the output here will be x of n minus 1, correct? Now x of n minus 1 should be multiplied with h of 1. So I have x of 1, n minus 1, that has to be multiplied with h of 1, and again even that should be given to an adder. Yes. So here is our adder, I am connecting it. Now what is the output of the summing point? So the output is h of 0 into x of n plus, what is the signal coming here? It is nothing but h of 1 into x of n minus 1, correct? Now moving on to the third parameter, x of n minus 1 is delayed again to get x of n minus 2. So we have x of n minus 1, delay it by 1 time unit, gives us x of n minus 2. Fine. X of n minus 2 should be multiplied with h of 2, and it should be given to an adder which is adding these two parameters. Yes. Multiply this with h of 2. So here is our adder whose first input is h of 0 into x of n plus h of 1 into x of n minus 1, and the second input to this adder will be h of 2 into x of n minus 2. So finally what will be the output of this adder? This was the output of this adder, the first adder. So coming to the second adder, the output of this adder will be h of 0 into x of n plus h of 1 into x of n minus 1. So this is the first input. The second input is plus h of 2 into x of n minus 2, correct? So we got this parameters. If I do the same thing for m number of times, and if I delay it for the last time, so we are going to get x of n minus m minus 1, so which has to be given to an adder, okay? And finally the output of this adder is nothing but equal to y of n. So this is how we can draw the direct form structure just by looking into the difference equation of the given FIR filter. So you need to expand the given difference equation, then start drawing. This is how we draw direct form realization with the help of difference equation. This structure has to perform m multiplications and m minus 1 additions. So this is very important, which we need to keep in mind. How many multiplications it is performing? 1, 2, 3 up to m, okay, from 0 to m minus 1 means it is m. So it is performing m multiplications, and the number of additions which it is performing is m minus 1. And this particular structure requires m minus 1 memory units to store m minus 1 previous inputs. Why? So this is our present, whereas this are nothing but our previous inputs. So it requires m minus 1 memory units to store m minus 1 previous inputs. So this direct form realization is also called as transversal realization, or it is also called as tapped delay line realization. So what are the two names for direct form realization? It is transversal or tapped delay line realization, okay. So this is all about direct form realization. Now let us start solving problems on direct form realization. This is the question that is given: h of z is equal to 1 plus 2z inverse minus 3z power minus 2 minus 4z power minus 3 plus 5z power minus 4. Draw direct form realization. So what they are telling, they are not indicating whether it is an IR filter or an FIR filter. So what we know in FIR filter, the transfer function of an FIR filter contains only zeros. Looking into this particular transfer function h of z, that is a system function, it is having only zeros. Therefore, the given transfer function belongs to FIR filter. So that is the first conclusion which we should make by looking into the given system function or the transfer function. And we all know h of z is equal to y of z by x of z, Laplace of output to the Laplace of input. Okay. Now, this is equal to 1 plus 2z inverse minus 3z power minus 2 minus 4 z power minus 3 plus 5 z power minus 4. Okay. Now, I need to find out the difference equation from this given function, that is, I need to find out the equation for y of n. For that, what let us do? Let us keep y of z in the left hand side and move x of z towards right hand side. Therefore, y of z will be equal to x of z plus 2z inverse into x of z minus 3z in power minus 2 into x of z minus 4z power minus 3 into x of z plus 5z power minus 4 into x of z. Okay, we got this equation. Now, in order to find out y of n from y of z, I should apply inverse z transform. So, apply inverse z transform. So, if we apply inverse z transform, y of z tends to y of n, which is equal to x of z tends to x of n plus 2 into z inverse into x of z tends to x of n minus 1 minus 3 x of n minus 2 minus 4 x of n minus 3 plus 5 x of n minus 4. So, this is the difference equation from which I should draw the direct form realization of an FIR filter. So, what I did, from the given system function, we concluded it is an FIR filter just by looking into the system function. We know that the system function of an FIR filter contains only zeros. Yes, the given system function contains only zeros, so we concluded it as an FIR filter. Then we know h of z is equal to y of z by x of z. I wanted to find out the expression for y of z, cross multiply x of z, then you get this equation. Then to this equation I need to apply inverse z transform. So, if I apply inverse z transform, this is the equation which I am going to get. Now, here we know y of n is our input, x of n is our output. Now, if I start with the input x of n, okay, x of n, the coefficient of x of n is 1. So, in the standard equation it was h of 0. So, now it is 1. So, x of n should be multiplied with 1 and that has to be given to a summing point. Okay. So, this is done. Now, moving on to the second term, x is delayed once. So, delay x once. Okay. This gives us x of n minus 1. What is the coefficient of x of n minus 1? It is 2. So, multiply this with 2 and connect it to an atom. Okay. Now, if I chuck the output of the summing point at this particular stage, it is x of n, so from this branch, and plus 2 into x of n minus 1. Okay, we completed these two parameters. Now, moving on to the third parameter, x of n minus 1 is delayed again. So, this has to be delayed once, gives us x of n minus 2. So, here is our summing point. Okay. Now, x of n minus 2 should be multiplied with minus 3. This has to be multiplied with minus 3 and that should be given to an adder. Yes. Now if we check the output of this adder, one input to this adder is this entire thing, that is x of n plus 2 into x of n minus 1. Okay. What is the second input? It is nothing but minus 3 into x of n minus 2. Yes. So minus 3 into x of n minus 2. Okay. We completed this also. Now x of n minus 2 should be delayed once in order to get x of n minus 3. So delay this once. Gives us x of n minus 3. This has to be multiplied with minus 4 and the previous summing point output should be given to the summing point and this also should be given to the summing point. Now if we check the output of the summing point, okay, so this is the output at this stage. This is the output of this stage. So if I check the output of this stage, so this is the entire thing which I am getting as first input. So this is our second input. So what will be the output at this particular point? It is x of n plus 2 into x of n minus 1 minus 3 into x of n minus 2. Then minus 4 is multiplied with x of n minus 3. So it is minus 4 x of n minus 3, correct. This is also done. So which is the last term? This one. So again this has to be delayed once. So if I delay x of n minus 3 once, this gives us x of n minus 4. X of n minus 4 should be multiplied with 5. X of n minus 4 should be multiplied with 5. And it has to be given to a summing point, okay, and the output of summing point is nothing but our y of n, okay. What is y of n? It is nothing but this one plus this one. So the expression for y of n will be x of n plus 2 into x of n minus 1 minus 3 into x of n minus 2 minus 4 into x of n minus 3. From this branch we are getting 5 into x of n minus 4 plus 5 into x of n minus 4. So are the equations same? So that is the equation which I got from the structure, that is with the help of this difference equation we draw this structure. Then if I verify the output of the structure, the output and the difference equation which we obtain by simplifying the system functions are same. So like this we can draw the direct form realization of an FIR filter with the help of difference equation. The second question is realize the system function h of z 1 by 2 plus 1 by 2 z inverse plus 1 by 2 z inverse plus z power minus 2 plus 1 by 4 z power minus 3 plus z power minus 4 plus 1 by 3 z power minus 5 plus 1 by 2 z power minus 6. So in exam what they do is they give a single system function and they will tell you to realize in all the three structures like direct form, cascade as well as lattice. So let us take the system function and let us try to realize it using direct form realization. So we know h of z is nothing but the transfer function and in the given system function we have only poles, therefore it belongs to an FIR filter. Therefore, h of z is equal to y of z divided by x of z, which will be equal to 1 by 2 plus 1 by 2 z power minus 1 plus z power minus 2 plus 1 by 4 z power minus 3 plus z power minus 4 plus 1 by 3 z power minus 5 plus 1 by 2 z power minus 6. Okay. Now I want the expression for y of z. So let us cross multiply x of z. So y of z will be equal to 1 by 2 into x of z plus 1 by 2 z power minus 1 into x of z plus z power minus 2 into x of z plus 1 by 4 z power minus 3 into x of z plus z power minus 4 into x of z plus 1 by 3 z power minus 5 into x of z plus 1 by 2 z power minus 6 into x of z. Okay. Now we got the expression for y of z. Now I need to find out the expression for y of n just by applying inverse z transform. So apply inverse z transform. So if I apply inverse z transform, y of n will be equal to 1 by 2 into x of n plus 1 by 2 into x of n minus 1 plus x of n minus 2 plus 1 by 4 x of n minus 3 plus x of n minus 4 plus 1 by 3 x of n minus 5 plus 1 by 2 x of n minus 6. So from the system function we obtain the difference equation. Now it is very easy to draw the direct form with the help of difference equation. So input is x of n. Okay. So input should be multiplied with 1 by 2. This has to be multiplied with 1 by 2 and that should be given to a summing point. Okay. Then this x of n should be delayed once. X of n should be delayed once. This gives us x of n minus 1. This should be multiplied with 1 by 2 and given to a summing point. So I am multiplying it with 1 by 2 and I am giving it to a summing point. So the output of this summing point is nothing but 1 by 2 x of n plus 1 by 2 x of n minus 1. Now x of n minus 1 should be delayed again. This has to be delayed. This gives us x of n minus 2. This x of n minus 2 should be multiplied with 1. The coefficient of x of n minus 2 is 1. So multiply this with 1 and feed these two inputs to the summing point. Now the output of this summing point is nothing but 1 by 2 x of n plus 1 by 2 x of n minus 1 plus x of n minus 2. Now coming to this one, x of n minus 2 should be delayed again. So this has to be delayed, gives us n minus 3. This should be multiplied with 1 by 4. Give it to an adder. So we completed until this one. Now the next parameter is x of n minus 4. Delay this once. Gives us x of n minus 4. This has to be multiplied with coefficient 1. Give it to an adder. Okay. We completed this also. Again x of n minus 4 should be delayed again. Gives us x of n minus 5. This has to be multiplied with 1 by 3. Okay. Again this is done. Last one is x of n minus 6. Delay x of n minus 5 once. Gives us x of n minus 6. This has to be multiplied with 1 by 2. And finally this is our y of n. Okay. So like this we can draw the direct form realization. Hope it is clear how to draw the direct form realization for any given system functions. The second type of realization is lattice structure for FIR filter. So previously we saw direct form realization and now let us see lattice structure. So this lattice structure is basically used in digital speech processing applications as well as in adaptive filters. So if we consider mth order filter, mth order FIR filter, its system function hm of z will be equal to a polynomial am of z, where am of z is a polynomial which is given by am of z, which is equal to 1 plus summation k ranges from 1 to m minus 1 am of k into z power minus k. So for m greater than or equal to 1, where a0 of z is always equal to 1. So this is a0 of z, that is always equal to 1. Now if I equate these two equations, so I can term it as equation 1, this be equation 2. So what I can do? Substitute equation 2 in 1. So what is hm of z then? hm of z will be equal to 1 plus summation k ranges from 1 to m minus 1 am of k into z power minus k. Okay. What they have done is, in few textbook they have termed it as a, in few they have termed it as alpha. So it is one or the same. And we all know that hm of z is nothing but equal to y of z by x of z. Okay. Instead of hm of z, I can substitute this. Yes, this is nothing but equal to 1 plus summation k ranges from 1 to m minus 1 am of k into z power minus k. Now I need to find out the difference equation, that is the output equation of the filter y of n. So I want the expression for y of z. So let us move x of z towards left hand side. So if we move x of z towards left hand side, y of z will be equal to x of z plus summation k ranges from 1 to m minus 1 am of k into z power minus k into x of z. If I apply inverse z transform to this, y of n will be equal to x of n plus summation k ranges from 1 to m minus 1 am of k into x of n minus k. Okay, let us term this as equation 3. If the order of filter is 1, that is if m is equal to 1, so let the order of filter, that is m be equal to 1. If m is equal to 1, then what happens to equation 3? Then equation 3 will have only one value, that is the summation part. So then there is no need to write the summation part. I can directly write m as 1. So if I write the equation, y of n will be equal to x of n plus a, the value of m is 1, the value of k is also 1, we are giving only one value for k, then x of n minus 1. If I draw structure to this, so we know x of n is the input, x of n. So I want the previous input also, so I will delay x of n once. Okay, now I should get this y of n, so which is nothing but the combination of x of n with some constant term multiplied with x of n minus 1. So I will term this constant term as k. So I will multiply this So what I will do, I will multiply this with a constant term k1. Okay. Therefore, y of n will be equal to the same equation, that is x of n plus a1 of 1 into x of n minus 1. For the purpose of simplification, what I will do is, I will consider the signal coming here as f naught of n. So, x is getting divided into f naught of n and here it is g naught of n. If g naught of n is delayed once, we will get g naught of n minus 1. Okay. Similarly, so let us give g naught of n minus 1 to a summing point. So, then let us multiply this f naught of n with k1 and let us give it to the summing point. So, here we will get g1 of n and here let us take the variable as y1. y1 of n is equal to f1 of n. So, what I have done? So, I am assuming x of n is getting divided into two signals, yes. So, I have termed the first branch signal as f naught of n and the second as g naught of n. So, here what I have done? I have delayed g of n once, so which gives us g naught of n minus 1. So, adding the signals from this branch and this branch gives us y of n, which I have termed it as f1 of n, and adding the signal from this branch as well as this branch gives us g1 of n. So, this is nothing but the lattice structure for the FIR filter when the order is 1. Now, similarly, let us check for order 2. This is structure for single stage lattice structure. Okay. If I write the equations with respect to this figure, let what we have assumed f naught of n is same as g naught of n, which is equal to x of n, correct? So, g naught of n and f naught of n are nothing but x of n, that is done. Now, what is f1 of n? So, f1 of n is nothing but the output of this stage. So, what is the input to the adder? It is nothing but f naught of n. The first input is f naught of n plus. So, what is the input from this branch? It is k1 into g naught of n minus 1 plus k1 into g naught of n minus 1. So, what is f naught of n equal to? It is nothing but x of n. So, this will be equal to x of n plus, let k1 be as it is, g naught of n is equal to x of n. Then what is g naught of n minus 1 equal to? It will be equal to x of n minus 1. So, did I get the same output equation? Okay. So, this is nothing but equal to y of n. Done. Now, let me check the expression for g1 of n. So, what is g1 of n equal to? So, we have from this branch it is k1 into f naught of n, k1 into f naught of n plus, and the second branch is giving g naught of n minus 1, g naught of n minus 1. We all know f naught of n is equal to x1, x of n. So, k1 into x of n plus g naught of n minus 1 is equal to x of n minus 1. So, these are nothing but the equations of the outputs of single stage lattice structure, that is f1 of n as well as g1 of n, and f1 of n is nothing but equal to our y of n. Now, let us do the same thing for order 2. For second order FIR filter, m is equal to 2. So, we know the standard equation for y of n, which is equal to x of n plus summation k ranges from 1 to m a m of k into x of n minus k. Okay. Now, the value of m is 2. So, let us substitute in this equation. So, x of n plus summation k ranges from 1 to 2 a m of k into x of n minus k. Now, let us expand the summation. So, x of n plus the value of m is 2 2 into 1, a2 of 1 into x of n minus 1 plus a2 of 2 x of n minus 2. So this is nothing but the equation for y of n. So now if I chuck the equation for the first order and if I write the outputs for second order, the equation of the lattice structure of the second order will be equal to y2 of n, which is equal to f1 of n plus k2 into g1 of n minus 1. In the first order we had it as f1 of n, which was equal to f0 of n plus k1 into g0 of n minus 1. Just I am rewriting in terms of f2. So the equation will be this. So then g2 of n will be equal to k2 into f1 of n plus g1 of n minus 1. So let us term this as equation 4 and let this be equation 4, let this be equation 5 and let this be equation 6. From the first order filter we know what is f1 of n and what is g1 of n minus 1. So let us substitute in this equation. We know that f1 of n is equal to x of n plus k1 into x of n minus 1 and g1 of n was equal to k1 into x of n plus x of n minus 1. So this were the equations which we obtained for first order filter, that is for lattice structure. Let us substitute in this equation. We want what is g1 of n minus 1. So in this equation wherever we have n, if I replace it with n minus 1, so replace n with n minus 1 in g1 of n. So what will be the equation? g1 of n minus 1 will be equal to k1 into x of n minus 1 plus x of n values n minus 1. n minus 1 minus 1 will be equal to n minus 2. Okay. Now we got the expression for f1 of n as well as g1 of n minus 1. So let us substitute both in equation 5. That is substituting f1 of n and g1 of n minus 1 in which equation? In equation 5. Therefore, f2 of n will be equal to what is f1 of n? It is x of n plus k1 into x of n minus 1 plus k2 into what is g1 of n minus 1? It is k1 x of n minus 1 plus x of n minus 2. Now let us multiply k2 inside the bracket. So if I multiply x of n plus k1 x of n minus 1 plus k1 into k2 into x of n minus 1 plus k2 into x of n minus 2. Now in these two terms I can take x of n minus 1 as a common factor. So this is equal to x of n plus k1 plus k1 into k2 into x of n minus 1 plus k2 into x of n minus 2. So this is the expression for f2 of n. So let us term this as equation number 7. Now if I compare equation 4 with 7, so this is a standard equation for a second order filter. So if I compare these two, what is the coefficient of x of n minus 1 here? It is a2 of 1 and here it is k1 plus k1 into k2. Therefore, so comparing equation 4 and 7, so the expression for a2 of 1 will be equal to K1 plus K1 into K2, or I can write this as K1 into 1 plus K2. What I have done, I have taken K1 as the common factor. So can I find out K1 from this expression? Yes. Therefore, K1 is equal to A2 of 1 whole divided by 1 plus K2. So this is nothing but the expression for K1. Done. Now, if I compare the coefficient of x of n minus 2 in equation 4 with the coefficient of x of n minus 2 in equation 7, comparing these two, what is A2 of 2 equal to? It is equal to K2. So, what we got? A2 of 2 is equal to K2. So, therefore, what we can conclude? We can conclude that the reflection coefficients K1 and K2 are called as the reflection coefficients of the lattice structure can be obtained from the coefficients AM of K and AM of M from that of the direct form structure. If I draw the structure for second order, so the first part remains as it is, x of n. So here it is f naught of n. So here it will be g naught of n according to our assumption. So we delay it once. So then we go for g naught of n minus 1. So here we will have an adder. Here also we get an adder. K1, K1. So this was our first structure, and here the output was F1 of n, and here the output was G1 of n. So now with the standard expression of the second order filter, so what I should do? I should give this directly to an adder. I should delay this once. That gives us G1 of n minus 1. Then this has to be multiplied with K2 and given it to an adder. Then again here it has to be multiplied with K2 and given to this adder. So the input to this adder is F1 of n plus K2 into G1 of n minus 1. That gives us F2 of n. Okay, this F2 of n is nothing but our output y of n. Therefore, F2 of n is nothing but y of n. Similarly, here we get G2 of n, where G2 of n is nothing but equal to K2 into F1 of n plus G1 of n minus 1. So this is the second order filter lattice structure. Okay. So therefore the conclusion is we can find out the reflection coefficient K1 and K2 of a lattice structure from the filter coefficients of a direct form structure, that is AM of K. The summary what we did is here, that is we can find out the coefficient of lattice structure from the direct form coefficients. Similarly, I can find out the direct form coefficients with the help of lattice coefficients. Okay. So these are the two important equations which we need to remember in order to draw lattice structure.